So good evening, Mexborough and Swinton. This is the end of everything, and as you can probably see from the subtitle there, I'm talking about the fate of the Earth, the Sun, the galaxy, and ultimately the fate of the universe. So if you'll forgive me paraphrasing Buzz, we're going to eternity and beyond. So after a little prologue, I'll be looking at the future of the Earth and the Sun and the solar system, and the far future of stars and galaxies, including our own galaxy. And I'll be looking at the far, 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 far future and the ultimate fate of the universe. That's going to get very depressing when we talk about the end of everything, so I'll finish with a little epilogue, which hopefully will be on a slightly more upbeat note. So just to put things in context, this is the end of everything, but if we dial the clock back to the beginning of everything, I'm not going to go through all of that talk, but we believe the universe started 13.8 billion years ago. It's expanding, and therefore if we wind the clock back, everything that we currently see in the observable universe, 100 billion light years across or thereabouts, everything used to be a lot closer together. If we wind the clock back far enough, everything that we now see in the observable universe used to be just a few centimetres apart. Difficult to imagine everything we see being compressed into one small golf ball, but we think that's how it all began. A lot of hydrogen was made, and in the last 13 or so billion years, some of that hydrogen has been converted by stars into heavier elements. Now, in order to get the timeline of where things are going in the future, I'm going to use these numbers along the top of the screen to try and keep track of where we are. In order for it to make sense, we're not going to go through year by year by year. Each box in the top here represents 10 times further into the future than the previous box. So we'll be looking perhaps 1,000 years into the future, 10 to the 6, 1,000,000 years, 10 to the 9, 1 billion years, 10 to the 12, 1 trillion years into the future. And I'm grateful for the work of Adams and Laughlin, who published a paper about, 25 years ago now, in which they tried to calculate various astrophysical phenomena and the timeline, the timescales on which those phenomena are going to occur. And I've used that paper to try and get my slides in the right order. I'm not, strictly speaking, talking about the fate of the Earth and then the fate of the Sun and then the fate of the galaxy. I'm looking at various things and putting them in a time-by-time chronological order. So we're going to skip a few years. Let's assume that we don't blow ourselves to pieces. Let's not worry too much about the fate of humankind in the next 100 or 1,000 years. Let's jump to the next thing that we know is going to happen on an astronomical timescale. We know that on timescales of order 10 to the 4 years, we know that the Earth's axis precesses, as indicated by that little graphic on the left-hand side. On a cycle of 26,000 years, the direction in which the Earth's axis points traces out a circle on the sky. So at the moment, we know the Earth's axis points close to the star Polaris, which is what we call at the moment the North Star. But of course that will change. In the time of the Egyptians, it was presumably Tuban over 2,000 years ago. And on a timescale of 10 to the 4 years, roughly halfway through the cycle, the North Star is going to change from Polaris to Vega. So that's going to make it much easier for Boy Scouts to point out which way is north, because they just have to find a really bright star, and that's going to be Vega in the sky, and that will tell them which way is north. But there are other consequences of the North Star changing. For instance, at the moment, we are closest to the Sun in January during northern winter because of the way the Earth's axis is pointing. But when the Earth's axis is pointing the other way in 10,000 or 12,000 years towards Vega, we are going to be closest to the Sun during northern summer. And that is going to exaggerate the seasons, which are partly, at the moment, mitigated by the fact that we're closest to the Sun during winter. When we're closest to the Sun during summer, a lot of the northern hemisphere is going to get more extreme seasons. And these variations in the Earth's climate, which are due to changes either to the Earth's spin or the way the Earth orbits around the Sun, collectively, these are called Milankovitch cycles. And we'll hear more about that shortly. On a timescale of 10 to the 5 years, the Voyager spacecraft that were launched in the 1970s are going to be passing through other solar systems. So they were launched in the 1970s, and Voyager 1, if you remember, did a flyby of Jupiter and Saturn, and Voyager 2 did a flyby of Jupiter, Saturn, Uranus and Neptune. And they are now leaving the solar system. This graphic shows that in the top left, Voyager 1 is heading off in the direction of the star Gliese 445 and will be passing through that star system on this timescale. At the bottom of the screen, Voyager 2 is heading off in a different direction and will be passing close to Ross 248, again on a similar sort of timescale. Pioneers 10 and 11 were launched earlier than the Voyagers, but they're travelling a little more slowly. And Pioneer 10 on the right-hand side of the graphic here is heading off in the direction of Aldebaran, and Pioneer 11 is heading off in the opposite direction towards the centre of the galaxy. Still on a timescale of 10 to the 5 years into the future, we know that ice ages are coming. From the historical record, we know that there have been repeated cycles of glacial ice age or interglacial warmer periods between the ice ages over timescales that seem to repeat on a timescale of order 100,000 years. The Earth entered a relatively warm period, an interglacial warm period, relatively recently, and therefore we know the next ice age will be due, if you like, on a timescale of order 10 to the 5 years. This is another manifestation of Milankovitch cycles. The ice ages come and go depending on changes to the Earth's orbit. We know that the Earth has been slowing down. The Earth used to spin quite fast billions of years ago, and bit by bit, day by day, well, not necessarily day by day, but decade by decade, the Earth is slowing down because of the tides raised by the moon. So at the moment, to keep our clocks synchronized with the rotation of the Earth, we add a leap second. Every few years, we've been adding a leap second for the last few decades or so. But as the Earth continues to slow down, after 100,000 years or so, the Earth will have slowed down to the point that instead of adding leap seconds every few years, we'll need to add a leap second essentially every day. In other words, the rotation period of the Earth will no longer be 24 hours. It'll be 24 hours and a second. So we'll have to add a leap second every day if we want to keep our clocks synchronized with the rotation of the Earth. We don't know when stars are going to blow themselves to pieces. We know massive stars will end their lives in a supernova, but we can't say exactly when that's going to happen. But one of the best candidates is Eta Carina in the southern hemisphere, a very massive star that appears to be very unstable. The nebula that you can see around it in this Hubble Space Telescope picture that was Astronomy Picture of the Day a few years ago, we know the nebula has been generated by the star sloughing off some of its outer layers, which it's been doing perhaps for thousands of years. And that tells us that this star is definitely getting rather unstable. So it's thought that this will probably terminate its life in a supernova on a timescale of 10 to the 5. Perhaps before that, but probably no longer than a timescale of 10 to the 5 years. It might be beaten to the punch by Betelgeuse. Here, a photographer has photographed the sky in Czechoslovakia and has doctored, if you like, the image to show what it might look like, what the sky might look like when Betelgeuse brightens in a supernova, and he's indicated in this picture what it might look like at night. It'll probably be bright enough because Betelgeuse is only some 600 or so light years away. It is probable that Betelgeuse will be visible during the day as well as a spectacular sight at night. And of course it'll ruin the constellation of Orion in the process. But it's not just supernova we have to worry about. There are some other stars, Wolf-Rayet stars, such as this one, an artist's impression of Wolf-Rayet 104. When they die, they might produce a gamma-ray burst. Wolf-Rayet stars are very unstable stars that might be precursors to supernova. This particular one is 7,000 light years away, 10 times further away than Betelgeuse, but it might still be a threat when it decides to die because the rapid rotation of these Wolf-Rayet stars can produce jets, and gamma rays can can flow out of these jets and produce a radiation burst, which is very powerful if you happen to be in the line of sight of one of these jets. Now, we don't know quite whether we are directly in line. It's difficult to tell. If we are unlucky enough to be in the line of sight when this star dies and produces a gamma ray burst, looks like we have a late admission. Let me just get rid of the annoying window. Okay, when this star does die, if it produces a gamma ray burst, if we happen to be lined up with the jet, then we could get a significant dose of radiation heading in our direction, and that could be a threat to life. More likely, we're not lined up directly with the jet, and so we're probably going to be safe from a gamma ray burst like that. On a timescale of 10 to the 6, 1 million years into the future, we can get a good idea of what our neighbouring stars are going to be doing in terms of their motion. The spacecraft Gaia has been mapping out star positions and star motions. It's a very accurate system for looking at star positions, and if it looks at different times, it can get an idea of how the stars are moving. All the stars are independently moving around the centre of the Milky Way, and so it might be that as we all go round the Milky Way, some of our neighbouring stars might venture rather close to us and then drift away again. And it's been calculated that one star in particular, Gliese 710, is going to get very close to us before it moves away. It's going to get close enough to actually come within the Oort cloud of our solar system. The Oort cloud stretches up to about halfway to the nearest star, of order a light year or so in size. When Gliese 710 does come that close, it is almost certainly going to disturb a lot of the tiny systems, the tiny particles. They're more than that. They're probably rocks. They could be large asteroids. They could be the nuclei of comets ultimately. But these bodies are going to be disturbed by the passage of Gliese 710 because its gravity is going to be not insignificant compared to the gravity of the Sun holding them in place. So when Gliese 710 comes into our region, it is certainly going to disrupt the Oort cloud, and it could send asteroids or comets heading into the inner solar system, and it could produce naked eye comets, perhaps every few weeks for 1 million years. It's going to be a significant disruption to the Oort cloud. It's not yet clear whether it will disrupt the rest of the solar system, but it will definitely disrupt the Oort cloud. And it's interesting to note that for a little while, our solar system will actually have two suns, our familiar sun plus Gliese 710. So it's not quite going to look like other double sun systems that we know of. Gliese is not going to be as bright as our sun, but it's interesting to note that we will be a two-sun solar system for a while. Still on a timescale of 1 million years, this is a picture of Meteor Crater, Arizona. This is not supposed to imply that we can expect an impact like that every 1 million years. This picture is there for two reasons. One, so that we can note, wasn't it really lucky that this impact just missed the visitors centre? Wow, that was close. But as well as that, it reminds us that any impact on Earth doesn't last forever. This particular meteor crater might only be tens of thousands of years old. Anything that's really old is probably going to get lost because the Earth's crust gets weathered by wind and rain, and impact features don't necessarily last. You could say, well, yes, that happens on Earth, but it doesn't happen on the Moon. Well, strictly speaking, not true, because, for instance, the footprints of the astronauts on the Moon are not going to last forever, not due to weathering in the sense of what happens on the Earth, but the Moon is constantly bombarded with micrometeorites. They're pulverizing the surface, and basically the footprints that we see at the moment are not going to be there forever. In another 1 million years, those footprints will be gone. On longer timescales, all of the Apollo hardware will eventually disappear because of the pulverizing effect of micrometeorites that are raining down consistently on the surface of the Moon. Moving to 10 to the 7 years into the future, we can think about what's happening with Pioneers 10 and 11. Remember, it'll only take them a few tens of thousands of years to pass to the nearest star. So on this timescale, they will have passed through hundreds of solar systems. And they might conceivably be picked up, in which case anybody who picks up the Pioneer spacecraft will see this plaque. And on timescales up to 10 to the 7 years, they should be able to read the plaque, which tells them we are the makers of this particular spacecraft. The picture on the left, this map of pulsars, tells them where we come from. And at the bottom it says we've launched this particular probe from the third planet from the Sun. So on this timescale, if they pick up the Pioneer spacecraft, they'll be able to tell its origin. But on longer timescales, this plaque will become too pitted and eroded. Why should that be if it's flying through empty space? Well, space isn't empty. It's full of tiny particles. It's full of dust, tiny grains of carbon and possibly silicon and a few other elements. These little specks might only be a few microns in size, but after you've spent 10 million years ploughing your way through the interstellar medium, eventually impacts from those tiny dust specks will make the plaque unreadable. So if it's not picked up in the first few hundred solar systems that it passes through, anybody that does pick it up will not be able to tell its origin. On a timescale of 10 to the 8 years into the future, we can ask what's the fate of, for instance, a dynamical system like Saturn's rings. Perhaps first we should ask, where do Saturn's rings come from in the first place? Is it possible that a moon similar in size to Mimas, for instance, actually disintegrated and made Saturn's rings? When you look at a moon like Mimas, you might think to yourself,
that's no moon. It's a space station.
Because that crater, Herschel, does indeed bear a striking resemblance to the form of the Death Star. But calculations have been done, the credit is on the left-hand side there. If you ask the question, what if we take a moon about the size of Mimas, take Saturn before it had any ring system, ignore all of the other moons, what if you were to pulverize a moon, let's imagine it smashed into a comet or something like that, what would happen to the debris cloud? You might assume that the debris cloud would simply continue orbiting Saturn just like the moon did in the first place. But actually what you find when you run the simulation is that very quickly the debris gets stretched out along the entire orbit. Note the time in the bottom right. It only takes a matter of days or weeks for a ring system to actually form. That's because all the individual tiny particles, all of the trillions of particles, are interacting with each other and bumping into each other and causing a change to the orbit. Very slowly, everything is drifting closer and closer to Saturn. So over millions of years, all of these particles have drifted inwards to form the ring system that we see. The structure is because of the gravitational influence of other moons. But this process is still going on. So if we run the clock forward 10 to the 8 years, all of these particles will continue to drift inwards and ultimately rain down onto the surface of Saturn. So eventually the ring system of Saturn will be no more. We are lucky enough to exist at a time when the ring system of Saturn is visible and very bright. For those of you who enjoy the view of Saturn, make sure you get in next time the rings open up, because you won't be able to enjoy it in another 100 million years or so. Still on a timescale of order 10 to the 8 years into the future, we have to remind ourselves that although we tend to think of planets going around the sun as being a sort of clockwork, and we fool ourselves into building orreries or tellurians showing how the moon goes around the Earth and the Earth goes around the sun, and if it's clockwork, we tend to think that's because the solar system is clockwork. We know where the planets were thousands of years ago. We know where the planets are going to be thousands of years from now. We can predict eclipses arbitrarily into the future. Well, perhaps not arbitrarily, because on a timescale of many millions of years, well, the solar system is chaotic. It is unpredictable once we get to these sorts of timescales. Not only can we not tell, for instance, where Jupiter is going to be in 100 million years, we don't even know how many planets there are going to be in the solar system. It could be Jupiter has decided to eject one of the smaller planets from the solar system. We think the solar system has rearranged itself in the past, and it might choose to do so again into the future. Like weather systems on planets, the solar system ultimately is chaotic. It's predictable on short timescales, but not on long timescales. Still on a timescale of 10 to the 8 years into the future. This is a map of what we think the Milky Way looks like. There's us, the Sun. You are here. We're sitting in a little bit of a spur in between two of the major spiral arms of the Milky Way. Because we're sitting in between two spiral arms, we're in a region that's not particularly densely populated with stars. But as the Milky Way rotates, as we go around the centre of the Milky Way, we are going to move from a low density region between spiral arms. We're going to move into a spiral arm where it'll be a much higher stellar density. So we're going to have many more stellar neighbours. At the moment, we haven't got many. For instance, if we think how many stars are there within, let's say, 10 light years of us, we've got a few. But there might be significantly more when we move into a spiral arm. What are the consequences of having a lot of stellar neighbours? Well, one of the consequences we've already seen. For instance, when Gliese comes close, it will distort the Oort cloud, and a number of bodies in the Oort cloud will end up raining down into the inner solar system and produce asteroid or comet impacts. And if there are enough of them, sooner or later, one of them is going to hit the Earth. We know that has happened in the past. If we look at how often species are exterminated as a function of time, this is the percentage of how many species disappeared from the Earth, we see that these spikes tell us that we've had extinction level events a few times over the last few 100 million years. And it could well be that this is linked to how often we move into or out of a spiral arm of the Milky Way. The last major extinction event on the right-hand side there, the KT event, that was the boundary between the Cretaceous and the Tertiary periods. That extinction level event, that's the one that killed the dinosaurs. Not all of the mammals, of course. Some mammals survived and eventually gave rise to us. But we can expect this to happen again on a timescale of 10 to the 8 years or so. In other words, this of course is just an artist's impression. We can expect large chunks of rock to come our way. In this particular case, it looks like there's a large chunk of rock heading towards, well, looks like it's heading towards Italy. That's definitely bad news for Italy, but of course if the chunk of rock is large enough, it's going to be bad news for the entire Earth. It's going to change our climate, it's probably going to result in the extinction of species. You could argue that it's almost inevitable that species will be exterminated. It's happened in the past, it will happen in the future. The big question is, will we be one of those species? Maybe we've got time to figure out what to do about protecting ourselves from really large chunks of rock coming in our direction. The second consequence of having a lot of stellar neighbours, as well as having lots of asteroids, is that if we've got a lot of stellar neighbours, one of them might decide to go supernova. At the moment, we haven't got many stellar neighbours, and those neighbours we have, none of them are massive enough to be supernova candidates. Remember, a star has to be considerably more massive than the Sun to end its life as a supernova. But once we have a lot of stellar neighbours, it's more likely that one of those stellar neighbours might go supernova. A supernova within 100 light years of Earth could be a danger to life on Earth. And it's been estimated that a supernova within 20 light years of Earth could, in principle, end all life on Earth. And if that sounds a bit alarmist, bear in mind that we have evidence that it's happened before. Supernovae that go off within 100 light years of Earth will leave a particular isotope called iron-60, which is generated by supernova and, as far as we know, is not generated by any other process. This particular element, this particular isotope of iron, has been found in Earth sediments. And iron-60 is unstable, it's radioactive, it changes over millions of years from iron into something else. It changes into cobalt and then into nickel. That means if you find any iron-60 isotope in the Earth's crust, in the Earth's sediments, it must have arrived relatively recently. It hasn't been there for billions of years because it will have changed over a timescale of many millions of years into something else. So the fact that we do see small amounts of iron-60 in Earth's sediments tells us that almost certainly a star has gone supernova close enough to deposit that element into the Earth's atmosphere and ultimately into the Earth's sediments. It's estimated that it would have to be within 100 light years. Anything more distant is unlikely to have any significant effect in terms of deposition of this particular element. So nearby supernovas have happened in the past. Almost certainly they will happen in the future. All of this time, the moon has continually been tugging on the Earth and slowing the Earth's rotation. So tidal friction slows down the Earth and it sends the moon to a larger and larger orbit. There's a sort of exchange, if you like, of angular momentum. The moon steals some of the angular momentum of the Earth and uses it to make its orbit larger. At this point, 10 to the 8 years into the future, the length of the day is now not 24 hours, the length of the day is now 25 hours. We're going to have to give up completely the idea of adding leap seconds to try and keep our clocks synchronized with the Earth. We may as well throw the clock out of the window and start decimalizing the hours rather than trying to fit them into factors of 12 or 24. As well as the Earth slowing down, the moon is getting further away from the Earth. And again, there are consequences to the moon moving away from the Earth. One of the, you could argue, trivial consequences, in other words, it's not important for the fate of the Earth, is that we'll no longer be able to see solar eclipses. That's a shame. The moon will be so far away that the disk of the moon will no longer be large enough in our skies to cover the disk of the sun. So, as indicated in the astronomy picture of the day on the right-hand side, it will still be possible to have partial eclipses. It'll still be possible to have annular eclipses where there will be a ring of light around the moon because the moon is not large enough to cover all of the sun. But from this point onwards, it'll no longer be possible to witness a total eclipse of the sun from the surface of the Earth. So again, for those of you who like eclipse chasing and like going around the world to see eclipses, make the most of what time you have, because in another billion years they will not happen unless you go off-world. But the second consequence, which is perhaps a little more important in terms of our existence, is that the moon has a stabilizing influence on the tilt of the Earth, the so-called obliquity of the Earth. Currently we're at about 23.5 degrees, the tilt relative to the perpendicular of the ecliptic, Earth's orbit around the sun. Historically, we think there is evidence that it hasn't changed by much more than about a degree. The cartoon on the left shows it rocking backwards and forwards to show you the extent to which the tilt of the Earth has changed. It's hardly changed at all for very long periods of time. But if the moon moves away from the Earth, its stabilizing influence will be lost. It'll no longer, as it were, lock the Earth's axis in that position, and the Earth's axis will be free to erratically move however it likes under the influence of other planets in the solar system. And it could change erratically, and of course if the Earth's tilt changes erratically, that means the seasons are going to be wildly varying and the Earth's climate again will be changing dramatically. Regardless of what influence we have on climate change, we know there are big changes coming on these timescales. Voyagers, I said earlier, are leaving the solar system, and just like the pioneers have a plaque to tell anybody who picks them up where the spacecraft came from, Voyager contains a gold disc. And just like the Pioneer plaque ends up getting pitted and eroded, so the Voyager's gold discs won't last forever. But they'll last longer. The gold discs on Voyagers will last perhaps 1 billion years. That's been calculated by how quickly the surface will evaporate. Gold-coated discs, why do they last longer than the Pioneer plaques, even though they're ploughing their way through the interstellar medium? Remember those dust grains that are going to be impacting? Well, true, they will be impacting, but not on the disk itself, because the disk is protected underneath a cover. and the cover is going to take the brunt of the impacts, protecting the gold disk and perhaps making the gold disk last for 1 billion years. So again, Voyager will have passed through tens of thousands of solar systems by the time it gets to the point where it will no longer be possible to read the disk. But perhaps even before that, there will be a problem, because although the disk is protected, the brunt of the impacts will be taken by the cover, but it's the cover that contains the instructions for how to read the disk. Maybe that's not going to be a problem. Maybe if the Voyagers are picked up by some intelligence when it passes through some of the thousands of solar systems that it's going to pass through, maybe anybody intelligent enough to pick up Voyager and figure out what it is will be intelligent enough to figure out how to read the record even without the instructions on the front cover. On a timescale of billions of years, the Sun is going to start to change. It's not yet a red giant, but the Sun's luminosity will start to change as it evolves and starts to move towards its red giant phase when the hydrogen in its core starts to run out. The Sun's luminosity will increase by perhaps 10% for every billion years from this point onwards. So it won't be long before there's so much radiation hitting the Earth, the surface of the Earth is going to get too hot for comfort. The surface of the Earth is going to be driven to something like 80 Celsius. The oceans are going to boil dry. So going underground isn't going to help us much. Perhaps we're going to have to leave the Earth until it's cooled down a little bit. We're going to have to find some way of existing beyond this point. Now, the Sun is going to expand until it's a red giant, and it's been calculated that over a few billion years, the size of the Sun, when it inflates into a red giant phase, is going to be comparable to the orbital radius of the Earth. So in other words, the surface of the Sun is going to approach the Earth. And you'd think, well, that's probably going to be a bit of a problem for us. But it's not actually certain whether the Sun is going to engulf the Earth, even if the Sun does expand until its radius is comparable to the radius of the Earth's orbit. And that's because as the Sun moves towards the red giant phase, it inflates and the solar wind is going to get much stronger, resulting in mass being lost from the surface of the Sun. So as the Sun approaches a red giant phase, it's going to lose mass, and hence the gravitational pull on the Earth is going to go down, in which case the Earth's orbit will increase. So the cartoon on the left shows what might happen. As the Sun gets larger and larger, the Earth is actually going to move away from where it used to be. So at some point, the size of the Sun is indeed going to engulf the original Earth orbit, but the Earth won't be there anymore. The Earth will have moved to a new orbit. Perhaps it'll end up somewhere like where Mars is now, for instance. So it's by no means absolutely clear whether the Earth will get engulfed or whether the Earth will survive the Sun going through a red giant phase. Let's assume for the time being the Earth survives. What's in store next? Well, the outer part of the Sun's atmosphere is going to be sloughed off to produce a planetary nebula, and what's left is going to be a very hot core of a white dwarf. Maybe it's going to be basically a lump of carbon. The Sun will have produced hydrogen into helium and helium into carbon, and at the end of its life, the white dwarf that's left is going to be principally made of carbon. It's going to be hot simply because it's the core of an old star, even though there's no longer any nuclear fusion taking place. So we've now passed the red giant phase. We're now talking about many billions of years into the future. If the Earth survives, it has another problem to contend with, and that is it's going to lose its magnetic field. Now, the magnetic field of the Earth is produced because we have a spinning molten core. And the core of the Earth is molten not because of the heat coming from the Sun, but because of the elements in the core. Radioactive elements are producing radioactive particles. They are releasing energy, which is keeping the core molten. And once that finishes, because the radioactive decay of elements won't last forever, on this timescale, there will not be enough heat generated in the core to keep the core molten. As soon as the core freezes, we no longer have a molten core that's spinning, we no longer have a dynamo, we no longer have a magnetic field. And once we lose that magnetic field, we lose protection from cosmic radiation. Perhaps this is what happened to Mars. Mars is a smaller planet, and this might have happened a long time ago for Mars. Maybe it lost its molten core a long time ago. If its core did freeze, it would have lost its magnetic field, and it's lost its protection, and hence it's lost its atmosphere. And that's why Mars is the way it is. If we survive the red giant phase of the Sun, if we survive the Earth losing its magnetic field and being exposed to cosmic radiation, trouble comes in threes, and the third problem in our future is that the Andromeda Galaxy is going to come crashing into the Milky Way on a similar sort of timescale, many billions of years into the future. So the Andromeda Galaxy is going to get closer and closer to us until it, like this image shows, this artist's impression, it's going to fill a huge chunk of our sky. So if you want to photograph Andromeda, you won't need a telephoto lens. If you wait long enough, you'll need a wide-angle lens to get all of Andromeda in, because it will be so huge in our sky. As the Andromeda Galaxy passes through the Milky Way, it's unlikely that any stars are going to collide with each other, so almost certainly the Sun will survive, but there will be a riot of new star formation as the gas and dust of one galaxy collides with the gas and the dust of the other galaxy. So it'll be really messy when the two galaxies pass through each other. Andromeda will come out of the other side, probably with its spiral arms heavily disrupted, and then eventually the two galaxies will settle together into one large elliptical galaxy. On a timescale of 5 billion years, it's thought that the two centres of the two galaxies will still be two distinct nuclei. There will be a supermassive black hole from Andromeda and a supermassive black hole from the Milky Way. Over time, those two supermassive black holes will orbit each other and eventually merge into one even bigger black hole. On a timescale of 10 to the 11 years into the future, the dance between the Moon and the Earth finally comes to an end, because one day, the rotation period of the Earth, will equal 1 month, the length of time it takes the Moon to go around the Earth. Which means the Earth will be tidally locked to the Moon. The same face of the Earth will always face the Moon, just like at the moment the same face of the Moon will always face the Earth. They will be always pointing at each other. There will be certain points on the Earth in which the Moon will always be in the sky, and there will be certain points on the Earth where you'll never see the Moon rise. So this is a result of the tides of the Moon on the Earth and vice versa, locking the two together. And if this picture on the right looks a little bit photoshopped, no, this is a genuine picture. It's a picture taken from a long way away by the Deep Space Climate Observatory. So we're looking at, as it were, a full Earth and a full Moon, but we're looking at the far side of the Moon, which is why it looks a little bit odd. We're now thinking about timescales of 10 to the 12, 1 trillion years into the future. We've already said that the Milky Way is going to merge with the Andromeda Galaxy. If we think about what's going on in the vicinity of the Milky Way, there are lots and lots of smaller galaxies, satellite galaxies around the Milky Way and indeed around Andromeda in what we call the local group. The local group comprises Milky Way, Andromeda, the Triangulum Galaxy, and lots of smaller galaxies. All of these ultimately are going to merge together. M31, M33 and the Milky Way are going to merge into one mega galaxy and hoover up all of the tiny satellite galaxies as well. It's not going to be, as that icon would indicate, a spiral galaxy. It's going to be one large elliptical galaxy. So they're going to collapse into one under the influence of gravity. But what's going to happen to all of the other galaxies? When we look out into the universe, we see trillions of galaxies. What's going to happen to those? Well, at the moment, we know that even because of the expansion of the universe, we know that some galaxies are receding from us at very high speeds. Some, indeed, are receding from us faster than the speed of light. That doesn't stop us imaging them. For instance, back in 2020, I imaged a quasar, a bright nucleus of a very distant galaxy. which was receding from us at twice the speed of light. It's now at a distance of some 25 billion light years, but it's still possible to image one of these objects. I took a photograph of it without using a telescope. I was just using my camera on a tracker. And of course, if we look on the right-hand side at the Hubble Deep Fields, we know that when big telescopes look into deep space, we see thousands of galaxies in a very small patch of sky, telling us that there are trillions of galaxies out there, many of them perhaps similar to our own Milky Way. But it's sobering to realise that because of the expansion of the universe, if we think of what's going to happen a trillion years into the future, all galaxies are going to be so far apart, expanding away from each other so fast, that it will actually be impossible to see any of these galaxies. So if in 10 to the 12 years' time a very intelligent race comes into being who decide to build themselves a Hubble Space Telescope and they look out into the universe, what are they actually going to see? Well, the answer is when they look into the universe, they are going to see nothing other than the stars in their own galaxy. They will not be able to see any of the trillion or so galaxies that we're able to observe from Earth, simply because the expansion of the universe will take them beyond their horizon. No matter how good their technology is, they will come to the conclusion, when they ask themselves, what is the nature of the universe? They will come to the conclusion the entire universe is just their own galaxy, whichever one that happens to be. They will have no clue that the universe is actually full of trillions of galaxies. That's a sobering thought. We live at just the right time to draw that conclusion. I said that the universe began 13.8 billion years ago, and that's where all the hydrogen comes from. We think it took about 3 minutes to make all the hydrogen in the universe. After a trillion years or so, the hydrogen is starting to run out. Stars have been taking hydrogen and converting it into other elements. Bit by bit, the hydrogen that was made in 3 minutes, after a trillion years, the hydrogen is running out. So what does that mean? Well, you need hydrogen to make stars. Well, as an aside, let me just say that some people don't think that's true. Some people think maybe you can make stars out of something else. Maybe you can make stars out of heavier elements. Can you take gas, which isn't made of hydrogen, but is made of heavier elements, and make stars from that? Some people think maybe, some people think no. But it's interesting to speculate that if you did make stars out of heavier elements, it might actually be possible to make stars which have fusion reactions going on at their core, but the surface temperature is much lower than you might expect. Not the sort of temperature that you would get in a red giant, thousands of Kelvin. Maybe you can have a surface temperature of only hundreds of Kelvin, perhaps even as low as 273 Kelvin. Is it possible to make a star in which the surface actually has ice? Well, it is thought that that is a possibility by some people. In other words, maybe it is possible to have frozen stars. And when I say frozen stars, I'm not talking about Disney's version of frozen stars, which is that picture on the left-hand side. So if that's the picture you've got in your head, well, let it go, because what I'm talking about is stars in which you have nuclear reactions at the core, but the surface is cold enough for ice to exist. That's only a hypothesis. A lot of people think, no, I don't think that's going to happen. You do need hydrogen. You have to have hydrogen to make the first stars. And when the hydrogen runs out, you can't make any more. It's just too difficult to make stars out of anything heavier. But before we can go any further, and yes, I would like to go further than 10 to the 12, I realise the red rectangle has come to the right-hand edge of the screen. But I want to go a little bit further, but we can't go further until we agree on what's happening to the universe. We need to think about how the universe is going to expand. So here's a graph of how it might expand. The relative size of the universe is the vertical scale as a function of time. And there are 4 coloured lines as to how the universe might behave. Each of those coloured lines corresponds to a certain amount of mass and energy in the universe. Now, we are clearly at the point labelled now with a relative size of 1. That's just a convenient unit to use. Notice that the age of the universe depends on which particular model we have as to how the universe is behaving now, how it will behave in the future, and how it has behaved in the past. If the universe has got an awful lot of matter in it, then we would be following the orange curve, in which case it would get larger for a while, but then because there was so much mass, gravity would get a hold of that and pull everything back together again, and we would end up in a big crunch where everything comes back to zero. The universe, if you like, will go through perhaps cycles of expansion and contraction, and then maybe another cycle of expansion and contraction. It would be a closed universe. But we don't think that's the universe in which we live. When I was young, we used to think we were on the green line. We thought the universe will expand and it will slow down and slow down and slow down, but continue expanding. But now, after the last few decades of observations, we actually think we're on the red curve. That's the best idea we've got as to how much matter and energy there is in the universe. So notice that the red line is not only expanding and doesn't seem to want to flatten off, but the gradient is getting steeper and steeper and steeper. The expansion of the universe appears to be accelerating for reasons that we don't really understand, and we're just calling it dark energy to pretend that we've got some understanding, but really we don't know why. So we can't predict the future other than at the moment it looks like we're on the red line, and the red line shows no signs of wanting to bend over. It's going to continue expanding forever. So if we bear that in mind, we realise that if we want to go into the future, effectively to eternity, we've got to change gear. Each small box in the timeline above now doesn't indicate 10 times further into the future, it indicates 1,000,000 times further into the future than the previous box. So we got up to 10 to the 12, 1 trillion years into the future. Now we're going to, 10 to the 30, 10 to the 48, 10 to the... I don't know if this is a zillion years or a gazillion years. I don't know what labels we want to give. We're just going to stick to 10 to the power very big numbers. So where did we get to before we took this little aside about making sure we understood what the expansion of the universe is going to look like? We said that on this timescale of many, many trillions of years, the hydrogen is running out. Stars might last for many, many trillions of years, especially the small ones. The heavy ones tend to not last too long, but the lightweight ones might last for very long periods of time. But even the lightest of stars don't last forever. So when the hydrogen runs out, what does that mean? There's no more hydrogen. You can't make any new stars. Stars don't last forever. The age of starlight will come to an end. There will be a time when there are no stars shining by converting energy, nuclear energy, into starlight. Those dead stars will continue to orbit. They're still there. They're just not shining anymore. The dead stars will be left drifting around like zombies. There will be white dwarfs, neutron stars, black holes. It might seem a bit odd to talk about white dwarfs not shining. Yes, they produce some light because they are hot, but basically they will cool down. And white dwarfs with no nuclear reactions at their core to keep them hot, they start off quite hot, tens of thousands of Kelvin, but it won't be long before they simply cool down and you will no longer be able to see them. Basically, white dwarfs will become black dwarfs if you give them long enough. They're just lumps of, well, probably mainly carbon. Some stars will be ejected by the galaxy. We see that happening anyway. Some stars are thrown out. Given long enough, lots of stars will be thrown out of the galaxy. And those that aren't thrown out will end up getting eaten by the supermassive black holes that seem to be at the cause of every galaxy. If we look at the magnetic fields, here they've been mapped out in a galaxy NGC 1097. They've been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy. That's the infrared telescope in the back of a 747, recently decommissioned. By looking at distant galaxies, we can map out the magnetic fields, and we think it's those magnetic fields that effectively funnel matter, whether that be dust and gas or even individual stars, into the supermassive black hole at the center of the galaxy. And therefore, eventually, supermassive black holes will eat up essentially anything around them. We're not sure what's going to happen to any individual atom. For many trillions and trillions of years, we know that atoms exist as positively charged nuclei surrounded by negatively charged electrons. The nucleus of an atom gets its positive charge from the protons, and we think protons are stable in that they last forever. But maybe they don't. If protons decay, in other words, change into different particles, then if they do, all atoms in the universe will fall apart. We don't know the timescale on which that's going to happen. On the relatively short timescales we're able to study protons, they look stable. And we don't think that if a proton is going to fall to pieces, we don't think it's going to happen on a timescale of less than the red box here, less than 10 to the 36 years into the future. But it might be from this point onwards, atoms disappear from the universe because protons decay. Even if protons don't decay, then atoms have only got a finite life ahead of them, because the only atoms that exist are in these black dwarfs. There's no atoms in neutron stars, there's no atoms in black holes. So the only atoms in the universe are in black dwarfs, and eventually black dwarfs will evaporate. That's a process that I'm not going to describe in any detail. But on this timescale, if you wait long enough, black holes evaporate to leave no atoms anywhere. We think black holes will continue to merge with each other. Any galaxies that are gravitationally bound, for instance, any of the thousands of galaxies that are in a galaxy cluster, those galaxies are going to merge, and the supermassive black holes at their centers are going to merge together. And they will grow. Our own black hole in our Milky Way is millions of solar masses. There are some galaxies with supermassive black holes of mass billions of solar masses. There's no reason why they don't merge together to give us supermassive black holes with masses of trillions of solar masses. It will happen if you wait long enough. But even black holes are not eternal. Even if you end up with a universe full of black holes and essentially nothing else, they will not last forever, according to our current understanding. They will evaporate. You have to wait for a ridiculously long time, which is why our red box there is now moving further to the right to a timescale of 10 to the power 66 years into the future. So why do black holes evaporate at all? There is a quantum mechanical process by which, in principle, you can borrow energy from nothing. Sounds a bit of a cheat, but we think this is the way it works. You can borrow energy from nothing and make matter and antimatter. You can make particles and antiparticles. And those particles and antiparticles will annihilate with each other and pay back the energy that you've just borrowed. In other words, you can borrow energy, make some stuff, which then annihilates with itself and pays back the energy again. Let's just see that again. We borrow energy, we make matter and antimatter, they annihilate very quickly thereafter and pay back the loan of the energy. We think that's happening all the time. How is that relevant to black holes? Well, when Stephen Hawking said, I wonder if that process could occur just outside the event horizon of a black hole, what might happen? And he hypothesized that what might happen is you generate matter and antimatter, and one of the two particles falls into the event horizon, into the black hole, where it of course can't get out, and the other particle escapes. So what you've done apparently is generate something which appears to be a net flux of something leaving the black hole. It wasn't actually that. It was generating these particles from borrowed energy. In a sense, you're borrowing it from the black hole, and then you're finding that half of it gets away and half of it gets taken back by the black hole. So this particular apparent flux of particles, or radiation, because the particles themselves will ultimately decay as radiation, this radiation has now become known as Hawking radiation. Hawking proposed it. We haven't ever seen it, but a lot of scientists believe, yep, this almost certainly must happen. The quantum mechanics tells us this ought to happen. The amount of radiation that you would expect from a black hole increases as the black hole gets smaller and smaller. So in other words, large black holes evaporate very slowly, but as they get smaller and smaller and smaller, they evaporate more and more and more quickly. So over time, a black hole evaporates and the radiation levels increase until it finally disappears in a flash of radiation as the last vestige of the black hole winks out of existence. Even the really big ones, even the supermassive black holes which lurk at the centre of galaxies which eventually will merge with each other, even they will evaporate eventually. But large black holes are very slow to evaporate, which means our red box has to be pushed all the way over to the right-hand end of the screen to give us enough time for these really big black holes to evaporate. It'll take trillions of times longer than some of the smaller black holes which will have evaporated a long time ago. So have we reached the end of time? Well, strictly no, but to all intents and purposes, yeah. If we think about 10 to the power 100, which is a googol, no, not that googol, the googol is just a misspelling. The one on the right is simply a misspelling of Google on the left. 10 to the power 100 is a googol. And after a googol years, it has been calculated the last black hole will have evaporated and there will be nothing but radiation. In other words, there is no mass, no matter left anywhere in the universe. There's just a trickle of radiation floating around. So at this point, from this point onwards, nothing happens. And so you could argue that time, the passage of time, becomes essentially meaningless. The universe will continue to expand, radiation will get stretched out to longer and longer wavelengths, but nothing is going to happen from this point onwards. And although we don't normally write out all the zeros, for this special case of 10 to the power 100, let's just remind ourselves what timescale we are talking about. There it is written out in full. 10,000 million, 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 million. You can do it yourself. It's an awful long time. It's impossible to imagine that length of time, but just because you can't imagine it doesn't mean you can't do the maths and do the calculations and work out how long it would take black holes to evaporate. And that's the answer you get, that sort of timescale. So it's not quite eternity, but as Woody Allen would say, eternity is a very long time, especially towards the end. Another way of looking at these ridiculous timescales is one of my favourite cartoons is XKCD, and they tried to put a human spin on this. They said a human is simply a system for converting dust billions of years ago into dust billions of years from now via a roundabout process, which involves checking email a lot. I thought that's an interesting way of sort of trying to get your head around. Humans are, of course, only around for a tiny fraction of the length scales, the time scales that we are talking about. So if that's got you all thoroughly depressed that everything is going to come to an end and the universe is going to end not with a bang but with a whimper, and everything is going to be dark and everything is going to be boring, let me finish with an epilogue just to try and brighten your day just a little. You could say that we live in a golden age. The sun is middle-aged and well-behaved. It's billions of years old. We've got billions of years ahead of us. The moon is at just the right distance to stabilise the Earth's axis and hence stabilise the seasons and give us a nice place to live. As a bonus, it also gives us the spectacle every once in a while of a total eclipse of the sun. Thanks to evolution, humankind has managed to explore and discover and understand the universe in which we live. And we've managed to do that by building spacecraft, which we've sent out to visit our closest neighbours so that we can understand them a little better. And we've built ourselves telescopes with which we can look out into the universe and see billions of galaxies at distances of billions of light years. We could not have done this in the very early universe because we needed lots of generations of stars. Generation after generation after generation were needed to make the heavy elements, to convert hydrogen into helium, helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron, and all of the heavy elements that we need for us to be us. And we've just seen that in the far future, trillions of years from now, the universe is going to be very dark and very boring. So you could say the best time to exist is now. Thank you for listening.